Hey darlings, welcome to our lesson on electronegativity. So for today you'll need the Unit 2 comic strip. It's found in your Unit 2 Section 3 packet. It's also found in your textbook. The textbook has a nice colored version, but if you're using your textbook, make sure that you have a separate sheet of paper so you can jot down some notes next to it. You'll need a pen, your periodic table, and Table S. So in this lesson we're going to go over what electronegativity is, the trends in electronegativity, and the bond types that happen with Ionic, polar covalent and nonpolar covalent in terms of electronegativity. So electronegativity is just how attracted an atom is to other electrons. You can find out if the bond is something called polar or nonpolar, or if the molecule is polar or nonpolar. So if a bond is polar, we're going to have to look at the electronegativity difference. So I'm going to use delta En to write that out. But all that means is your electronegativity value from table S for one element minus the electronegativity value for the other element. So you're just trying to find out what the difference is in electronegativity. And you'll use table S to help you out with that. So make sure you jot down that it's table S. For your molecule, if you're determining whether the molecule is polar or nonpolar, you're going to look at its shape or molecular geometry. So hopefully you've looked at that. If you haven't, take another peek at the molecular geometry video, and also work with the models in class as well. So we are going to use table S, and just to kind of remind you what we're looking at, the electronegativity values are listed right here in this column. They don't have a unit, and for some of these you'll be able to kind of remember what some of the electronegativity values are. For example, hydrogen is 2.2, carbon's 2.6, oxygen's 3.4, and our most electronegative element out there is going to be fluorine with an electronegativity value of 4.0. So let's take a look at this cartoon part, and this is not in your textbook, but this is probably going to be in the video. So we're going to interpret what is going on in this picture. First of all, we have a penguin. It has the letter H in front of it, or on it, so we can assume that that's going to be hydrogen. The polar bear here is chlorine. And they each have their hand on an ice cream cone. So we have to see here what's happening with the ice cream cone. So they are still sharing the ice cream cone, but the chlorine is kind of taking it over a little bit more. The hydrogen has less of the ice cream cone. We also see that the ice cream cone also has 2 scoops of ice cream on it. These scoops, just to give you a hint, represent the number of electrons. So, since there are 2 scoops, there's 2 electrons here. And the chlorine is kind of pulling those 2 electrons closer to itself. So, I know it's kind of a weird interpretation, but I'm kind of helping you out when it comes to figuring out what this comic strip is trying to tell you. Over here on the left-hand side, we have the structure of HCl, and we have this arrow right here. This arrow represents the dipole. And the dipole is just the 2 poles, meaning one end is positive, the other end is negative. So since chlorine, the polar bear, is taking more of the negative electrons, it's taking more of the ice cream cone, it actually has more of a negative charge. So we call it a partially negative charge. This happens to be a lowercase delta, so I'll draw it up over here. That's partially negative, partially positive. So the chlorine is a little bit more negative. That makes the hydrogen a little bit more positive. We can also call that electropositive, like we call chlorine electronegative. We also see that hydrogen is a little bit more positive because right over here, this arrow shows us a little plus sign. So that shows us that hydrogen is a little bit more positive. So we're going to go through this comic strip. This is going to be a long video, so I apologize, but I'm going to help you kind of figure out what this all means. So it's called the Bare Essentials of Polarity. In case you haven't found it in your book, make sure you find it now. And it says you don't have to go to the ends of the earth to find polar molecules. They're all over the place. A polar molecule is just a molecule with a difference in electrical charges between 2 ends. So let's make sure we highlight that. Polar molecule is a molecule with a difference in electric charge between 2 ends. Also make sure that gets down into your notes as well. The next one says polarity in molecules is caused by a difference in electronegativity between atoms. So polarity caused by a difference in electronegativity. And this is when table S comes in handy. We can find out what those values actually are. It also says electronegativity describes the ability of an atom to attract bonding electrons towards itself. And in this case, the electronegativity, or the electrons, are represented by the number of ice cream scoops. So this here shows us the bonded pair of electrons. Since there's two scoops right there, there's a pair of electrons or two electrons. Down here it says chlorine is more electronegative than hydrogen, so the bonded pair of electrons in HCl spends more time near chlorine. So chlorine's value, we can look that up on the table S, and see that its value is higher than that of hydrogen. So there's more electrons that are going towards chlorine. This diagram over here shows us the partial charges, and they should show partial charges because hydrogen's not completely positive, chlorine's not completely negative, but they're partially negative and partially positive. Alright, so the bottom image shows us that we have this kind of like iceberg here. So electronegativity values tend to increase as you move northeast on the periodic table and decrease as you move southwest. So let's take a look at these, the animals that are here. We have penguins on this side and polar bears on this side. Let's also take a look at the relative sizes of each of them. So down in the penguin section, this little guy is probably the teeniest, tiniest little penguin there. The higher or the larger penguins are around here and here. Let's take a look at the polar bears. There's small little polar bears over here, and the largest polar bear is right there. We also have this keep out section. So that keep out section represents the noble gases. They don't usually have electronegativity values because they rarely bond to other atoms. So this iceberg is showing you the periodic table. I'm going to erase all these. So it's showing you the periodic table. Squint a little bit if you need to see it. The left-hand side's a little bit less in electronegativity value. The right-hand side's higher in electronegativity. And the noble gases don't have any electronegativity values. Okay, so on the next page, when two atoms with different electronegativity values bond, the bonding electrons spend more time around the more electronegative atom, creating a partial negative charge on that atom. The other atom has a partially positive charge, and the bond is considered polar. So, we consider this polar because that penguin still has its little hands, or whatever, flippers, on the ice cream cone. They're sort of sharing it, but most of the electrons are spending its time near chlorine. So that's why the penguin, the hydrogen, is partially positive, the chlorine, or the polar bear, is partially negative. So here we're showing the difference in electronegativity values. When atoms with equal electronegativity values bond, they form nonpolar bonds. The electron attracting strength of each atom is the same. So we'll highlight nonpolar bond, equal electronegativity value, and we have the same strength. So here we have two polar bears, relatively pretty much the same size, arm wrestling. Neither one is winning. They each have the same strength, equal electronegativity. On the right we have two penguins arm wrestling. They each have the same strength. One is not winning over the other. However, when you put a polar bear and a penguin together playing arm wrestling, the chlorine is stronger. It has a higher electronegativity, and so it ends up winning, and the penguin ends up losing. It has less electronegativity. So here we show that the bond is a polar bond. So we'll show more sharing here, equal sharing. Because the elements have such varying electronegativities and can bond in many different combinations, there is a really continuum of polarity and bonding. We can break the continuum down into three categories. So the first category is nonpolar covalent. We show that there's equal sharing and between the identical atoms. So the clearest example of nonpolar are those between identical atoms, such as H2, N2, O2, Cl2. Hey, we know these. These are our Hunkelgriffs, or our diatomic molecules. So we have H2, O2, N2, Cl2, Br2, I2, and F2. Bonds between atoms with nearly the same electronegativity, such as carbon and hydrogen, can also be considered nonpolar. So carbon and hydrogen will also be nonpolar. So we'll put a carbon-hydrogen in there too. So these 7 Hunkelgriffs plus the carbon and hydrogen, if we have bonds between 2 hydrogens, 2 oxygens, or carbon and hydrogen, they're all going to be nonpolar. Now we're not talking about the bond between the H and the O. That's not correct. It's just the bond between 2 hydrogens. In this case, we have a bond between 2 oxygens. They're relatively equal in strength. Same thing with these 2 hydrogens. Also notice the number of electrons. The hydrogens will share 2 electrons. However, oxygen ends up sharing 4 electrons. Draw your Lewis dot diagrams in case you need help with that. So that was nonpolar. This is polar. Polar covalent. We show that we have partial positive and partial negative charges. 2 atoms share bonded, they still share the bonded electrons, but unequally. The electrons are more attracted to an atom, one atom than another, so they're more attracted to the one that has a higher electronegativity value. So this is between carbon and oxygen, or between hydrogen and fluorine, and hydrogen and chlorine like we've seen before. Alright, here are ionic bonds. And we've talked about ionic bonds back in Unit 1. So ionic bonds, if you notice here, what is happening with the ice cream cones? Instead of the 2 animals sharing them, the chlorine has taken it and made a run for it. So chlorine is taking over those 2 electrons. It's not sharing them at all. Same thing with ionic bonds. The nonmetal will take the electrons, and the metal will end up being more positive. Okay, so make sure we get this information down. The metal ends up being positive, and let's make sure that we write down that that's a metal, which in this case is sodium. The chlorine is a negative charge, that's the nonmetal, or the anion. This was our cation, or the metal was our cation. So a large difference in electronegativity results in a winner-take-all situation of ionic bonding. The more electronegative atom takes the bonding electrons and becomes a negative ion. This is when we're going to see ion. We can't use the term ion in covalent bonds. While the other atom becomes a positive ion. The opposite ions attract each other. So, polar bonds between atoms create dipoles, and that's what that arrow was that we showed you before. The word dipole can refer to the polarity of highlight this, the word dipole refers to the polarity of an individual polar bond, the net polarity of individual polar molecules that may have several polar covalent bonds within it, and the polar molecule itself. So there's 3 different definitions for dipole, but pretty much we're just going to see which ends up being a little bit more positive versus more negative. Let's take a look back at the dipole arrow. This creates a positive for us, so it's a partially positive side. So whichever atom has that little part of the arrow closest to it, that's the partially positive. The arrow head refers to the partially negative part of the atom. So we have N2 molecule isn't a dipole and doesn't have any dipoles because it's sharing its electrons evenly. The bond itself is nonpolar, and we can tell that by looking at the electronegativity values on table S. And this is really messy, but it'll be neater on your notes, sorry. And we'll say that the molecule is nonpolar as well, because this is a symmetric molecule. It has symmetry. The N on this side is the same size as the N on this side. Also notice, between nitrogen, if we do its Lewis dot structure, we show we have electrons being shared, but we have 1, 2, 3, 4, 5, 6 electrons being shared. If we look at the number of ice cream scoops, we have 1, 2, 3, 4, 5, 6. There's 6 electrons being shared equally between the two. HCl has a dipole and is a dipole, so the bond itself is polar because if we take a look, they have 2 differences in electronegativity values in table S. The molecule is polar because the Cl is larger than the H. It's asymmetric, meaning if you fold it upon itself right here, it wouldn't match up evenly. And here we have CO2 has 2 dipoles, but the CO2 molecule itself is not a dipole, meaning it doesn't have differences in charges. So the bonds themselves are going to be polar because they have an electronegativity difference. Sorry about that. The electronegativity difference in between the oxygen and the carbon is pretty big. So the oxygen will end up taking more of those electrons. Same thing with this oxygen. That means it cancels each other out for the overall molecule. Plus, if you fold it upon itself, it ends up being symmetric. So the molecule is symmetric, and therefore nonpolar. H2O has 2 dipoles. Because of its bent shape, it can also have a dipole in the sense of overall polarity. If we were to show the Lewis dot electrons, right here and here, there's more electrons. There's more electrons over on those oxygens, and so the arrows point towards it. The hydrogen ends up having a more positive charge, and that's why you have that part of the arrow towards it. The molecule itself is polar because, again, there's more electrons on the oxygen. If you were to cut this in half, it's not going to be symmetric. Alright, so the polarity of molecules can affect many of their other properties, such as their solubility, meaning how well they dissolve in water or alcohol or something else, their boiling points and melting points, and their odor. So hopefully read up the rest of that. Let's take a look at the electronegativity scale. This is also in your textbook, but these values are pretty similar to that of Table S, but these are the ones from your textbook right here. So we'll show that, just like we saw in the first page of the comic strip, over here, bottom left-hand corner has the smallest in electronegativity, that's francium. Fluorine has the highest. We can round that to 4.0 like the Regents does on your reference tables. So we show a continuum with the electronegativity difference, and there is a little difference between what the textbook says and what the Regents says. So I'm going to show you that here. When we want to see if the bond is polar, nonpolar, or ionic, we are going to take a look at the electronegativity difference. So the bond, we'll write down the bond, if it's polar, nonpolar, or ionic. And we're going to write delta En, meaning that we're going to subtract the values. So when you draw this out, start at 0, go over to 4, in the middle is about 2.0, and over here is about, let's see if that's 1, that's 0.5. So I just kind of wanted to show you guys where everything was. Around here is, let's see if that's 0.75, okay, that's about 1.7, right around there. So from 0 to 0.5, if the electronegativity difference when you subtract the two values is from 0 to 0.5, we consider that nonpolar. It's still a covalent bond. From around 0.5 to about 1.7, your textbook says 2.0, but the Regent says 1.7, so use the Regent's value. That's polar. And above that is ionic. This is a continuum, so if you notice the book's image, and this is why I have the book's image, it shows it's shaded in. So really, the more in this direction you go, the more ionic it is. So they'll ask you multiple choice questions. Which of the following is more ionic in character? Subtract the electronegativity values, and whichever one is the highest, will be the most ionic in character. So you can still have a polar bond, but this side ends up being a little bit more ionic. This side ends up being a little bit more nonpolar. So let's go ahead and calculate the values for each of these. I have table S for you right here. If you can't read it very well, make sure you get out your own table S. And we have 4 different examples here for us. So I have Cl and Cl. So find the electronegativity column. It's right there. And we want Cl and Cl. So it's 3.2 minus 3.2. When you subtract the two values, that is equal to 0. So look back at the continuum that we just drew. That should be nonpolar. Let's go ahead and take a look at the second example. We have carbon and oxygen. Carbon is 2.6. Oxygen is, if we look at it, find it, 3.4. So we'll subtract the two values. Don't worry about any negatives. We just want to see what the difference is. That is equal to 0.8. And if we look on the continuum, that ends up being polar. So it's a polar covalent bond. Most of those electrons are going towards the oxygen, and carbon ends up being a little bit more positive. We have hydrogen and chlorine. So hydrogen is 2.2. Chlorine is 3.2. When you subtract them, we have a difference of 1.0. And in the continuum, that ends up being polar. And then we'll do our fourth example. Hydrogen is 2.2. Fluorine is 4.0. So go ahead and subtract them. That should equal to about 1.8. And according to New York State, that's going to be an ionic bond. So even though that hydrogen and fluorine are both going to be nonmetals, hydrogen can act like a metal. In this case, it's going to be an ionic bond. But note that fluorine, or hydrogen and fluorine, ends up being the most ionic in character. So to summarize, electronegativity is just how attracted an atom is to electrons of another atom when it's in a bond. And we have a scale. Make sure you memorize those numbers on the scale. We have 0 to 0.5 is going to be nonpolar. 0.5 to 1.7 is polar. And anything above 1.7 is generally ionic. If we want to find the difference in electronegativity for a bond, oops, sorry about that, darlings. We'll go back through. Alright, so if we want to find what the bond is, oops, we'll go back. That's okay. I'll just do it on this side. So if we want to see if it's polar or nonpolar, we have to look at table S, the delta electronegativity, or the electronegativity difference, that continuum from 0 to 4.0. Here is 0.5, that's about 1.7. So these three sections. So over here would be nonpolar, here would be polar, that would be ionic. So that's just figuring out if a bond is polar or nonpolar. To figure out if a molecule is polar or nonpolar, you have to look at its shape. If it's symmetric, it would be nonpolar. If it's asymmetric, sorry about that, that's going to be polar. Okay? So make sure you get those notes down about each of those. If you have any questions, just please let me know. Take care, guys. Bye.